intelligence, maybe it's got an even greater challenge than we thought. Okay, let's recap on the lecture from last week. And the key thing we started off with was defining what an intelligent system might be. It's not relying on human analysis. We have a system, which I'll draw as a box, and the training of this system is applying data and applying the answers. And what we hope inside this structure is that a functionality emerges which will map the data to the answers. So after training, we have an emerged functionality. Now, first thing, the system should work on the data it's been trained on. If it doesn't work fully on the data it's trained on, it's unlikely to work on unseen data. The key operation is having got the functions from a training set, you then have a testing phase, and the testing phase is where you apply new data. And when I say new data, it is of the same description as the training data, but it is slightly different. Imagine faces going in. We might have 100 faces going in the training. We can test it on those exact same 100 faces. If it works, that's a good indication. But the real test is applying new images of the face, same face, but different data. And then from that, hopefully the answer emerges. And that is a standard learning system. Right. And looking at this general principle, we've got to have this property of generalization, because the system not only has got to recognize the data it's been trained on, it's got to recognize unseen data. So it must generalize. So that is a key property. Now, to get started on systems that generalize, we first of all were looking at heuristics, which are rules which we can apply to the data. And the simplest one, which I talked about in some detail, was the shape factor. It's a simple definition. Shape factor S is equal to perimeter squared over A. And this is sometimes called compactness. And if I was to ask you to do a quick test, in the class I'd come and look over your shoulder, but I can't now. But here's a quick test. Shape, which is 2D by D. And it's a rectangle. The shape factor for that quickly. You might be able to do it by inspection. Give you 10 seconds to think about it. The horizontal side is twice the length of the vertical side. The shape factor is going to be the perimeter. Oh, no! Come back. Still with me? Right, the perimeter is going to be 2D, 3D, 5D, 6D. So the perimeter squared is going to be 6D all squared divided by the area, which is going to be 2D squared. Sorting that out, we're going to get 36D squared over 2D squared. The D's cancel, the size is eliminated, and the answer comes out to be 18. And if you compare that to the example I gave you last week, which was a perfect square, the square was 16, and the circle was 4 pi, which was approximately 13. So a different shape, a different shape factor. Right, now if you've been doing some reading on shape factor, you will find on the notes, if you do a Google search, they don't use this simple version of the equation I've used. You have most probably come across S equals perimeter squared divided by 4 pi times the area. Now, if you come across that, this is the normalized shape factor. And the normalized shape factor, this 4 pi here, is the shape factor of a circle. The circle is the most compact shape. So instead of having a circle at 13, if you're dividing the shape factor by 4 pi, then the circle will have a shape factor of 1, and all the others will be reduced. So instead of ranging from 13 to however large the shape factor is, the normalized version goes from 1 and increases. Now, it doesn't matter which one you use as long as you're consistent. So the one I started off with is as good as any, as long as you realize it's not normalized, i.e. the most compact shape is not 1, it's going to be 13. We saw problems with calculating the shape factor on an image, and we realized that we have to use high resolution to get accurate shape factors, extracting the information from the picture. The other topic I looked at last week was run coding. And the run coding is a coding of the rows or the columns of an image. And it is for an image, a series, if that's black, it's first of all a series, get off, get off. It is a series of white runs, W11, followed by a black run, B11, followed by the second white run of the first row, which is W12. And we do that for a series of scans of the image, and it is coded. And that actual algorithm is the fundamental algorithm for image compression. But we're not using it for compression, we're using it for image representation. So as an example, if I gave you a run code of 2, 3, 1, 3, 1, 1, 2, 2, 1, 0, 4. If I gave you that run code, we can go back to the image. First of all, you've got to know the resolution of the image. So the resolution is 5 by 5 cells, pixels. Now, taking that run code, we divide it into runs of 5, which is going to be 2 and 3 is 5, 1, 3 and 1 is 5, 1, 2, 2 is 5, 1, oops, that's gone wrong. Let's take a naught out there. Let's have a naught 5. That will do. Right, now taking that to reconstitute the image, the first run is going to be taking a 5 array. We're going to have a run of 2 white ones and a run of 3 black ones. So that corresponds to that. We're now going to have a white, 3 black, and a white. Then we're going to have the third row is going to be 1 white, 1 white, 2 blacks, 2 white. Sorry. And the last one, no white, 4 blacks. So it will be that and a final white run of 1. So that's reconstituting the image. And the application I gave you was inspecting bottles on a conveyor belt, where you've got to do a vertical scan. There is a bottle which is good. There is a smashed bottle, something like that. Doing a vertical scan, you can match them using a run code. Now, simple question. If you're doing a vertical scan with a camera, how do you get a camera to do a vertical scan of an image? Simple answer, turn the camera 90 degrees. Okay, that covers where we were last week. So new material now, chain code. Another data compression method for images. And a chain code is a coding of the edge of an image. And we're still thinking of very simple images, usually black on white shapes. A shape like that. And of course, that would be on a pixel array. We're not to the complexity of faces or pictures yet. So the chain code operator, it operates on a pixel.
Yeah, I joined, bro. I literally joined.
Sorry. Hello, can't hear. Hello.
I think they asked a mistake.
Mistake?
Yeah.
Mistakes?
No, it's fine.
Right.
No, John, I think keep going.
Keep going. Bring the mistakes to the next face-to-face and we'll sort them out. In fact, I introduced my mistakes deliberately so that you have to think about them, okay? Right, the chain code operator. Oh, don't you do that to me. Oh, I hate these whiteboards.
Sorry, John, you need to go through it.
This system has an intelligence of its own, and it is very thick. It's not intelligent at all. Right, the operator, let's see if I can pick it up from there. The operator is a single pixel, and you simply note the directions of the neighboring pixel. And there's going to be 8 of them. Those are the 8 directions. And you have to label these directions. Now, the obvious way of labeling them, there are 8 of them, would be 1 to 8. No. 0, 1, 2, 3, 4, 5, 6, and 7. Why 0 to 7? 3 bits. I need 3 bits to represent the neighboring direction. 0 to 8 would require 4 bits, and it would take up more bits. So, as a human, we can use the chain code on an image. Just to show you how it works, I'll go to a 5 by 5 again. Again, these examples are very trivial. Real examples, it would be 1,000 by 1,000 pixels or more, 4,000 by 4,000 perhaps. But 5 by 5 will enable you to understand what it's about. Let's put an image in there. Again, I'll fit it easily on the array. So we've got no noise issues. In real life, we would have noise issues. That's 1, 2, 3, let's take it down to 4. In fact, I've got to make the array slightly bigger. Let's make it a 5 by 6. Now, yes. Oh, can nobody see my whiteboard?
Oh, we can see it. We can see it.
Yeah, we can see it.
Why is somebody not seeing it, Tatiana's? Can you help? No, Tatiana's gone. She's not feeling very well. Nothing I can do, I'm afraid, from this end. Yes, you come and see me when we're face to face, and I'll go over any problems. Okay, fine. Right. The operator, this operator here starts initially on that cell, the first one. And remember, with images, the origin is the top left, not the bottom right, as you would have in normal graphs. So this operator is sitting on this first pixel, and you scan it to find the direction of the neighboring pixel. 0, no, 1, no, 2. So that is the first entry in the code. You then move to the next pixel, start scanning, and you will see the neighbor is in direction 3. We move there. The next neighbor is direction. What did I put a 7 down there for? That's silly. That should be 4. We've now moved in direction 4. We're there. The next one is 5. The next one is 6. The next one is 0. And the final one is 0 before we get back to where we started from. Now, with a simple image like this, it doesn't save much data because the original image would be a 5 by 6, 1, 2, 3, 4, 5, 6, which is 30 bits. And the chain code, we're using 3 bits for each direction. It will be 3, 6, 9, 12, 15, 18, 21 bits. But if you take much larger images, the saving becomes much more significant. So that is the chain code done by a human. Now, when we start to try and do this in a machine, there is a problem because you have to start the scanning. You might not have realized this, but it was obvious doing it as a human. You have to start the scanning outside the image. And when we get down to, say, this cell here, if I would start scanning from 0, I would find 0 was an edge. And the system would lock up and it wouldn't move from those 2 cells. Now, it's quite obvious to a human that shouldn't happen, but a simple algorithm, unless you ensure that the scanning of the operator starts from outside the image, it's going to lock up and not work. So the algorithm. Initially, find first pixel, image pixel, which is, of course, the first one. Scan from direction 0. Move to next edge pixel. And here comes the important step. When you move to the next pixel, don't scan from direction 0, scan from direction. Let's change color for that. D bar plus 1, where D is the direction of the last move. So in the case of my first step, I was in this cell here. I moved in direction 1. Direction 2, sorry. So the algorithm says don't start scanning from direction 0, scan from the opposite of 2, which is 6, plus 1. So we start scanning for this pixel from there. And of course we go around and we find the next neighbor. Now that is no different from what we was doing as a human, but when it becomes important is when we are underneath the image. For example, if I start here, when the operator is sitting on that pixel, if I were to start scanning from 0, it would lock up in the image. But if I start scanning from the opposite direction to the one I've moved last time, the move was in direction 4. So I start scanning from the opposite of 4, which is 0, plus 1. I start scanning from direction 1. And let's put a blue color in there. That would be start scanning from that pixel there. And when we're underneath the pixel, because we're moving, and scanning from 1 plus the opposite direction plus 1, we will never enter into the image, and so you will scan the outside. And so that works, and you repeat. Oh, no, come back. 5. You repeat until back to first pixel. And that is the idea of the chain code. Now, personally, I don't think it's a particularly good coding. It's working on the coding of the edges, and we've seen from the shape factor, edges are noisy. So the accuracy and the repetition of a chain code on a given object is not particularly high. But it does have certain rotation properties. You can rotate the image 45 degrees, and that would be the equivalent of adding 2 to the chain code. You can also start at any point in the chain code, and if we shift this through a shift register, we can still get a matching. So there's the chain code, and it is used, but it's we can do better. Oh, this thing's disappeared now. Oh, makes me cross. Come on. It's not me who's changing the magnification. At least I am, but I'm touching something accidentally, I suppose.
John.
Yeah.
Is it possible to go over the algorithm with an example again, please?
Yeah, sure.
Thank you.
Right, let's take another example. I'll do it as if it was a machine, a computer program doing this. That's what, 6 by 6 is it? Let's take an image. There we are. It's fitting the pixels exactly. Let's see if I can get a bit. Right. There's my operator. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, and 7. Right. It's sitting there. Oh, come back. It's initially sitting there. That operator is the red square there. First direction is 0. First entry in the chain code is 0. We move to the next pixel. There. Next direction is 0. When it is sitting in this position, if I were to start at 0, it would appear the neighbor would be above. But the algorithm tells me I start from the direction I moved. Sorry, I'm wrong. Oh, damn thing. Start again. Top. Image there. Scan from 0. The direction is 4. 0, no. 1, no. 2, no. 3, no. 4. So the first entry in the chain code is 4. I then move to this cell, and this is the key thing to remember. I've moved. The previous direction I moved in was 4. If I were to start scanning from direction 0, we would immediately detect this as the next edge pixel, and it would lock up and it wouldn't go any further. But we have to move in the direction, the opposite of the direction we've moved in, which was at D bar. 4 was the direction we moved in. The opposite is 0, plus 1. So for this pixel, the operator will start scanning from this cell. 0, no, 1, no. So it starts scanning from 1. 1, no, 2, no, 3, yes. And the next entry would be the 3. We then move to the next pixel there, operator sitting there. We've moved in direction 3. We start scanning from the opposite of 3 plus 1, which will be 0. No, 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 yes. And that is direction 4. We then move down to here. We've moved in direction 4. We start scanning from 1. 1, 2, 3, 4, 5, 6. Direction 6. Move there. We moved in direction 6. We start scanning from opposite of 6, which is 2 plus 1, 3. And direction 3 is there. No, no, no. Yes, it's direction 6 again. Move to there. We start scanning in the opposite of 6, which is 2 plus 1, 3. 0, 6. 0, 1, 2, 3. We start scanning from there. No, 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 no. Yes, no, no, yes. The next one will be 0. And then opposite of 0 is 4. We start scanning from 5. Sitting here, it's going to be sorry, I've lost myself now. We were there, and that gave me direction 0. We move there, we start scanning from the opposite of, which will be 1. Start scanning straight away 1, that's the next code, and then the next one will be 0. Okay, essentially always start scanning from the outside of the image. Okay, so that's the chain code. Now, another coding. And this is only for rectilinear images. And what do I mean there? Images with straight edges. And so it's really industrial shapes. And if I take an image, and that's shaded in. Scan the image and find the first part of the image, the first pixel that is not white, which will be black. And we define a direction from which we will note an angle, and we measure a length. So we proceed along the line. This will be R1, and this angle will be θ1. When we come to the discontinuity, new edge, new direction, we start scanning from this direction to get the angle θ2, and the length will be R2. From this one will be θ3, and this will be R3. This one will be θ4, and this will be R4, and finally θ5, which will be almost 360 degrees, θ5 and R5. So the image, which was a picture, now becomes a series of lengths, R1, and angles, θ1, R2, θ2, R3, θ3, R4, θ4, and R5, θ5. Now that's a simple concept, but it's almost impossible to do directly on images. Why? Because there's no such thing as a straight line in a pixel image, unless it is horizontal, precisely vertical, or precisely at 45 degrees. Anything other than those three directions will be a staircase, and these edges will fragment into a series of vertical and horizontal directions. The only way this particular strategy will work is if we have a human encoder. Somebody operating on a screen, the image is placed in front of them. Call that point A, call that point B. Click on point A and click on point B. That will give you the coordinates. Normally for images it's IJ. It will give you the coordinates of A and the coordinates of B. And from that, if we've got those 2 points, this will be I1, IA, JA, and IB, JB. You can work out this distance R1, and that will be simple Pythagoras. It will be the square root of IA minus IB squared plus JA minus JB all squared. And if you want the angle is going to be tan to the minus 1 of JA minus JB over IA minus IB. And once you've got that, you've got a polar vector encoding. It's used for industrial shapes, but it does have the severe problem that you have to identify manually the discontinuities before you can get the R theta pairs. So that's around, but it's not a particularly good method. So that's pretty disappointing until we come on to the last method, which is brilliant. Don't you disappear on me. Oh, I'll start again. And the final method, gosh, I'm running out of time. It is the polar vector shape descriptor. And this takes images to vectors. And most of our neural networks and distance classifiers need vectors. This is the way you do it. Right, I've sort of run out of time. I think I better pack up there and we'll talk about the polar vector shape descriptor at the next lecture, which I hope will be on Monday. And I think it might be face-to-face, but Tatiana will confirm that. Okay, are there any questions at this point? Have to apologize about the appalling IT that you've had to suffer, but I've been suffering as well, so we'll have to try and overcome it. Any questions? Okay, catch up with me next time we're face-to-face and I'll go over any points